All right, so this lecture's topic is on membrane dynamics and transport. We're talking about each cell. The cells are the functional units, and they are surrounded by this membrane, kind of like a boundary for them. Allows them to keep the functioning in-house, and the cell keeps it somewhat of a division. And so we're going to talk about the dynamics of this membrane and also the transport, because the cell can't live solitarily. It has to move stuff in and out, and we'll see that doing when we look at transport across the plasma membrane. So you remember our cells. Our cells, they got this membrane, and it separates them from the outside. So the cells have this intracellular fluid, and everything outside is that extracellular environment. It's kind of like the bridge, because most of our cells don't have access to the external environment. The extracellular fluid is basically the transition between the outside and the cells. Okay, so there has to be communication between this fluid so the cells can operate and function properly. There has to be some kind of communication and also some kind of transport across there. The body fluids, this water lies, about 67% of the water lies inside the cell, another 33%, the rest lies extracellular, and only about a fifth of that is plasma, and the rest is the interstitial fluid that bathes the cells. Okay, because remember, these are all solutions. These are watery environments with solutes dissolved in them. So internal environment. All right, here's our cells. Most of our cells don't have access to the external environment. We have changes taking place, we are losing water, we need to gain water, or so forth, or we need nutrients. And so these cells are dependent on this extracellular environment because they don't have contact to exchange with the outside world. Okay. So the ECF, like we said, serves as that let me get this out, serves as the transition between the external environment and the internal. Okay. And you can see why homeostatically this ECF stays relatively stable so these cells can operate properly. If there's big drastic fluctuations, the cells are going to start to have problems. Okay, so let's look at the cell membrane. What comprises of that cell membrane? What is that boundary? Okay. The cell membrane, we got the main component is those phospholipids. You remember those phospholipids we saw in it's got that polar head with the tail. All right, and what we see in the cell membrane is it's mainly composed of a bilayer. Okay, here's one phospholipid, the other phospholipid. The polar sides face either inside the cell or outside the cell with those non-polar lipid components, fatty acids, facing the inside. Okay, this gives this cell membrane a non-polar characteristic to it. Also found floating in these lipids is this cholesterol. Okay, there are also carbohydrates and proteins that are embedded in this membrane. Okay, but the big draw is a phospholipid. Okay, that's the main component, and again, it gives us this cell membrane a non-polar, or at least an internal, a non-polar characteristic. Right? This is made chiefly of phospholipid and then some sphingolipids, but the big chief component is those phospholipids. Right. Here is rendering of that plasma membrane. There's those phospholipids. Okay, there's the tails. Okay, again, giving it a nonpolar characteristic. And so if you remember solubility, nonpolar things like to dissolve in nonpolar things, but nonpolar things do not like to, or polar things don't like to interact with nonpolar. Okay, so that gives this membrane characteristic a selective permeability. You can imagine if the membrane is nonpolar, polar things are going to have trouble moving through this membrane. Okay, so two main characteristics are going to determine whether something can move through the membrane. It has to do with polarity, okay, or size. Okay. Nonpolar things more easily move through the membrane, and small things more easily move through the membrane. Okay, so stuff that is permeable are small nonpolar molecules. If you remember, we talked about steroid hormones. They are made from cholesterol, very nonpolar. They can zip right through this membrane. Okay, another small molecule but polar, water. Water is kind of unique in that it can wiggle its way through here and make its way through. But big stuff, big macromolecules, big proteins that are polar, they can't make their way through here. They can't get through. They are turned away. And then even though ions are single or couple atoms, they are small, but what are they? They are charged. They're not even just polar, they are charged molecules. So they are repelled by this non-polarity of this membrane. So ions are not allowed through the plasma membrane. Okay, so because it is selectively permeable. Things that are non-polar, small, more easily to move through, right? Things that are large and polar are definitely not making their way through, and just even small charged ions can't make their way. They are turned back from this plasma membrane. We are going to see that your cell needs to get some of these items that can't make it through the plasma membrane directly. They need to get in. And so this is where we're going to be talking about the transport, how the different molecules get through the plasma membrane. How can we move stuff in and out of the cell? The cell's always got to be moving stuff in, getting many times waste products out. So we got to have this movement across this selectively permeable membrane. So it's pretty evident that we got to move molecules across the membrane. We got to get stuff into the cell and we got to get stuff out of the cell. Okay, so what drives this, or what are the components that make this take place? Okay, how can they move across? We got two main categories that determine how this takes place. We have physical requirements. Okay, this is what we were talking about, the membrane being selective. Okay, small nonpolar stuff can zip through that nonpolar membrane. Okay, can go directly through the phospholipid bilayer. Okay, and we'll take a look at that. What about stuff like ions? We're going to see that ions have to, sodium and potassium, we want those to be able to move in and out of the cell fairly regularly. Especially we're going to see for our neurons, it's a requirement to make them work. Okay, so to do that, there's got to be membrane proteins that span the membrane. And now our little ions can move in or out through these membrane proteins. And we're going to see for large stuff, we're going to need to use vesicles. We'll talk about that. The other component is energy requirements. Does the cell have to use energy, or can it just use, well, we're going to see concentration gradient. So if it requires energy from the cell to move a molecule either in or out of the cell, it is considered active transport. And if it does not, it is considered passive. Okay, so we're going to look at these different mechanisms in which we move molecules either in or out of the cell across the membrane. So here's kind of our map of how membrane transport takes place. We got down here physical requirements, and down here we have energy requirements, or sorry, up here we have energy requirements. Let's look at energy. No use of, so this is the passive portion. The cell does not have to use ATP, doesn't have to use energy to move the molecules. Okay. We have two forms of this. We can do simple diffusion or facilitated diffusion. You see the key word here is diffusion, okay, because this is going to make it passive, this diffusion. We're going to see where that energy comes from, right? Active transport, we have primary, secondary, and then we also have endocytosis, exocytosis, and phagocytosis. These all require energy. Okay. As physical requirements, simple diffusion, we can go directly through the lipid bilayer. Facilitated, secondary, and primary, we have to use membrane proteins, and then you can see these endocytosis, exocytosis, we have to use vesicles. Okay, so this is what we're walking through. This is the direction we're heading in, and we're going to describe all of these components here and how and what is required to allow these processes to take place, to allow transport across the cellular membrane, across that lipid bilayer. Right? So we're going to be talking the term, we already saw the term diffusion. And diffusion, we're going to need a concentration gradient. We talked molarity a bit in the chemistry. What does molarity tell you? Molarity tells you how much is dissolved. What is the concentration of a solution? Okay, how many molecules of each, okay, are in the solution? It's molarity. Just to go back, kind of rehash this, is we have a molecular weight. We have glucose. Let's look at the molecular weight. We got 6. Molecular weight of carbon is 12.01. The molecular weight of oxygen, there's 12 of them, or sorry, hydrogen. There's 12 hydrogens, so that's times 1. And then there are 6 oxygen, and the oxygen weighs almost 16. So we get a total of 180 for the molecular weight. So if we were to make 1 molar solution, this is the weight of 1 mole, right here, 180 grams. So if we wanted a 1 molar solution, we would have to put 180 grams of glucose into 1 liter of solution. Okay, and that gives us our concentration. Say if I put 360 grams of glucose in 1 liter of solution, now I would have a 2 molar solution. I would have a lot more glucose molecules in that 2 molar. I'd have twice as many molecules of glucose in that 2 molar than I would in the 1 molar. Okay, and what you got to realize is when these molecules, these glucose molecules, are in solution, okay, they're not just sitting there stagnant. They have what's called kinetic energy. This movement energy. They are bouncing around. All right? They're not sitting still, they are bouncing around in the solution. Okay, smaller things move faster, bigger things move a little bit slower, but they all have kinetic energy. They are moving around in the solution. They are not sitting there stagnant. Okay, because we're going to see, we talked about how the cell, there's passive transport and active transport. In passive transport, the cell doesn't have to use energy. And we'll see, because the energy comes from this kinetic movement and these molecules, right? And to do that, though, to get movement of a molecule in a certain direction is we have to have what's called a concentration gradient. We have to have a difference of concentration, say, outside the cell compared to the concentration of a molecule inside the cell. Okay, because that is going to be the driving force. We're going to look at what drives diffusion, what drives these molecules in a certain direction. Okay, just more on, there's my 1 mole of glucose, 180 grams, and I bring it into a solution that is 1 liter. Don't worry so much on molality. You may hear molality. When our biological systems were using such small concentrations that these are roughly equal molarity and molality. So just realize there's a difference. Okay, if I have higher molarity and a lower molarity here, I have a difference in concentration of a certain molecule. So let's look at the process of diffusion. Okay. In diffusion, remember these molecules have kinetic energy. Okay. And these molecules, the kinetic energy drives them from an area of higher concentration to an area of lower concentration. Okay. It's kind of like if you're in a club. Say you're in a club with a ton of people. Do you want to? Some people want to get stuck, but most people, they don't like to be crammed up. That's kind of what the molecules are when there's higher concentrations. They're all cramped up. So what do they try to do? They try to move to an area where there is more room, where there is lower concentration of molecules, or in the club, lower concentration of people. Less people in one area. Okay, and so that is the driving force in diffusion. But to have diffusion take place, I got to have a higher concentration of a molecule over here and a lower concentration of a molecule. I have to have what's called a concentration gradient, a difference in concentration between these two regions. Okay? Because the molecule is going to move from an area of high concentration to an area of low concentration. When they do this, it is called moving down or with the concentration gradient. Okay, diffusion is moving down the concentration gradient, going from high to low concentration. Okay, the driving energy is the kinetic energy in the molecules, the movement of the molecules. Okay, this is why cells don't have to use energy. The key is there has to be a gradient though. If the concentration out here is the same as the concentration inside the cell, there's going to be no net movement of molecules. Okay, there's got to be a difference in concentration between those regions. Okay, when does it stop? When would diffusion stop? You can see here, hey, I have water, there's no dye, put this cube of dye in, it goes to the bottom. Now there's this high concentration of dye here and very little concentration of dye out here. But what happens? The dye starts moving out from the area of high concentration to areas of lower concentration. Eventually, the dye, there'll be equal amount of concentration here and throughout the flask. That is when it comes to equilibrium. So diffusion takes place, if allowed to, it will take place until the molecules reach equilibrium in the solution. And this is just kind of gives you the rules of diffusion. In diffusion, it is kinetic energy of the molecular movement of the molecules is the driving force. Again, there has to be a concentration gradient because the molecules will move from higher concentration to lower concentration, going down the concentration gradient, going from high to low, going down the concentration gradient. It will continue, as we said, till equilibrium, till the molecules up here are equal to here. That's if it's allowed to go fully to equilibrium. Let's look at some factors that affect how fast diffusion takes place. Okay. Higher concentration gradient. Say I have a 3 molars over here, and over here I have 1 molar. Okay. If I have 2 molar and 1 molar over here, which one's going to move faster? The molecules in the 3 molar are going to move faster to here than, say, a solution that's 2 molar compared to 1. There is a bigger or higher concentration gradient. Okay. Shorter distances. Okay. So if you want diffusion to take place rapidly, you don't want this big large gap, all right, to move across. Shorter distances, diffusion takes place faster. Higher temperatures. Remember the kinetic energy. You can imagine these molecules at one temperature. If you increase the temperature, the molecules are going to move faster and therefore are going to diffuse much faster. And also smaller molecules. Okay, bigger molecules, kinetic energy, don't. Smaller molecules are bouncing rather quickly and therefore they diffuse much quicker. Okay. The last one, diffusion takes place in an open system, kind of like we did with the dye. It was all in one system, or across partition. This is what we're concerned about because we have a partition. Our partition in our case, when we're talking biology, is that cell membrane. So that cell membrane keeps a area where in intracellular fluid, and outside the cell membrane is the extracellular fluid. Okay, if we have a difference in concentration of a molecule from inside the cell to outside the cell, that would allow diffusion to take place as long as the molecule can move through the membrane. Okay, so that's where we're moving towards, is this diffusion that's taking place across the plasma membrane. Okay, so let's first look at simple diffusion. We already defined physical requirements. If you see diffusion, what's that telling you? It's telling you it is passive transport. The cell does not have to exert energy. The energy comes from the concentration gradient, high to low concentration gradient. Okay. In simple diffusion, okay, because there's simple diffusion and facilitated diffusion. They both are passive transport or passive movements of molecules, but what's different is in simple diffusion, the molecules can move directly through the plasma membrane. So what kind of molecules can do simple diffusion? We already said the plasma membrane is selectively permeable, and what's allowed to move through it? Directly through the actual plasma membrane. Small things and usually non-polar. Water's an oddity in that it's polar, but it's small enough that it's able to move through. So simple diffusion can take place as long as the molecule can move through, and the diffusion portion tells you that there has to be a concentration gradient. Say I have lots of steroid molecule outside the cell and very little inside the cell. Steroids, very nonpolar, allowed to zip through the membrane, and therefore there's a concentration gradient, and I have a small nonpolar molecule. I can do simple diffusion and move through the membrane. Okay. So remember, lipid-soluble molecules. They can move directly through the membrane. Okay, since this molecule is moving from here to here, where do I have higher concentration of, say, let's put a molecule here. This molecule is moving through the membrane. Where would my high concentration be? Yeah, my high concentration for this molecule would be, there's my little molecule, high concentration, and the low concentration would be here, because what's taking place, the molecule, if for diffusion to take place, is going from high concentration to low concentration. Okay, so simple diffusion. Diffusion tells you there's got to be a concentration gradient between outside and inside. Okay, sometimes the gradients, sometimes it's high outside, low inside, and sometimes it's high inside and low outside. Just depends on what molecule we're talking about and what the gradients are. Okay, but diffusion tells you there is a concentration gradient. The simple portion tells you the molecule can move directly through the membrane. Okay. So let's look at properties of this simple diffusion across a membrane. Rate of diffusion. Okay. Surface area is larger. Okay, membrane is thinner. Remember, longer distances, it's harder for diffusion to take place, so this would be much faster. Already said concentration gradient. A larger concentration gradient, bigger difference, going to make the molecules move faster. Okay. Is the membrane more permeable? So this is an added component in that we have to determine whether the molecule is permeable to the membrane. Okay. And what determines membrane permeability? We've already discussed some of this in that lipid soluble, more permeable, molecular size, smaller, usually much faster, and one we didn't discuss, lipid composition of the membrane, but this can change. But we're going to worry more about this here, molecular size and lipid solubility. Small lipid soluble molecules can move very quickly through the membrane. Stuff like cholesterol and steroids, very not polar and small, they can zip right through the membrane. Now let's look at a kind of specialized form of diffusion that takes place, and we're looking at water moving across the plasma membrane. Okay, and water movement or diffusion is termed osmosis. Okay, what are the requirements for osmosis to take place? Okay, is the concentration of solutes on two sides of the membrane have to differ. The membrane must be impermeable to some solutes, but permeable to water. Impermeable, or the other term used is non-penetrating, not able to penetrate the membrane. Okay, so you have to have one side that has more non-penetrating solutes than you do on the other side to get osmosis to take place. These non-penetrating or impermeable solutes are what termed osmotically active solutes, because they are the ones that are going to determine if osmosis takes place. Okay, in this you're going to have to think about osmosis almost in the reverse direction, because what you see is usually we're talking about solutes moving, things that are dissolved in water. Now we're talking about water moving. So water, if osmosis is basically a form of diffusion, water is going to move to an area of high concentration of water to an area of low concentration of water. But look at this up here. There's a higher concentration, the purple is the solutes, and there's a lower concentration of solutes over on this side. All right. Say this is the same volume. This is the same amount of solution on this side as it is on this side. Which of these solutions has a higher concentration of water? if these solutes take space, there's less space in this solution for water than there is in this one. So this is almost thinking in reverse. Solutes, if the solute was moving across, the solutes would go from here to here. But think about water. Higher concentration of water is on this side because there's less solutes, there's more room for water, there's a higher concentration of water, and lower concentration of water here. So water is actually going to go in this direction. Osmosis takes place in this direction. Okay, whereas if we were talking about the solute moving across, it would be in this direction. Okay, so you got to think about this almost in reverse because we're talking about the solvent moving, not the solute. All right, so let's learn some terminology and what's going to dictate. We've already discussed molarity. Molarity tells me how much of a certain molecule are in a solution. Okay, 1 molar solution, I have 1 mole of solutes in there. 1 mole of solutes in a 1 liter solution. Okay, what is going to dictate to compare, to figure out where osmolarity takes place? We have to compare terms called osmolarity. We got to compare osmolarity of the solution. All right, and this differs only if the solute is ionic. Because what happens to, say, NaCl? Does NaCl stay as NaCl when I put it in water? What did we learn in our chemistry? No, this divides into Na plus and Cl. Okay, osmolarity takes this into account. Okay, so osmolarity is molarity. Say I have a 1 molar solution of NaCl, but when I put NaCl in that water, what happens to NaCl? It becomes a sodium and a chloride ion. So in ionic compounds that divide, now I have 2 particles per molecule. Okay? Therefore, I have to times my molarity by 2, and a 1 molar NaCl solution will have 2 osmoles. Okay? Let me erase this. Now let's take a 1 molar solution. Whoops. 1 molar solution of glucose. Glucose is covalently bonded. Does glucose, is it like an ion? Does it break off into multiple particles? No, the glucose molecule stays intact. So for each molecule of glucose, I only have 1 particle. So for covalently bonded molecules, what do I have? I have 1 molar of glucose. I times it by 1 because it stays as 1 particle. So 1 molar of glucose equals 1 osmoles. All right. So if I had, say, 1 osmole on this side, 1 molar solution of glucose on this side, and it's partitioned between 1 molar of NaCl solution, the molarity is the same between these two, but if I calculate osmolarity, I have 1 osmole, and this solution would be 2 osmoles. All right. In this instance, if we're comparing osmolarity, water is always going to move for osmosis. It's going to move to the higher osmolarity. I do need to make one other caveat here, is that these solutes, if NaCl and glucose are not permeable, this is what takes place, or a non-penetrating solute. Because all we're going to care about for osmolarity, see it in a bit, is it's non-penetrating solutes that matter for. All we got to take into account is the osmolarity of non-penetrating solutes to determine where osmosis is going to take place. Okay, so let's also introduce some terminology when we're comparing solutions. All right, let's compare, say, two solutions. I have solution A and solution B. Solution A is 1 osmol, solution B is 2 osmols, and solution C is 1 osmol. Solution A, if I compare solution A to B, this solution has less osmolarity. So solution A is below osmotic to B. It's below its B's osmolarity. How about A versus C? It's termed same isoosmotic because they have the same osmolarity. When I'm comparing this, I'm comparing just osmolarities. Okay? We're going to introduce a term called tonicity. Tonicity is related, but it's not, there's no values. If we want to compare osmolarities to the solutions, all I got to do is look at the number, and that tells me what it is. If we went reverse with B, solution B has 2 osmols, solution A 1, so B is above the osmolarity of A. It's hyperosmotic to solution A. So what we're going to be doing is comparing solutions. In our case, what solutions are we going to be comparing? Solutions inside the cell, solution outside. Intracellular fluid, extracellular fluid. All right, because those are our two compartments, and that's what we're looking for, whether osmolarity will take place into the cell or out of the cell. Or sorry, osmosis, not osmolarity. Osmosis will take place into the cell or out of the cell. So let's see how this operates. Again, I want to tamp in that what we are comparing is the difference in osmolarity between non-penetrating solutes. Water will move to the area where there is a higher osmolarity of non-penetrating solutes. Okay? I don't care about penetrating solutes. If the solutes can move through the membrane, don't care about them. All I got to worry about is my non-penetrating solutes. All right? Let's look at this. Sucrose. We have a membrane here. We have a solution with 360 grams per liter inside the membrane and 100 grams per liter of sucrose outside the cell. And what this sucrose, I will tell you, is non-penetrating. It cannot move across the membrane. So we care about the osmolarity. If I was to calculate the osmolarity of this solution compared to this solution, what would it be? This solution, since it has 360 grams, is double of this. The osmolarity would be double inside the cell compared to outside. Okay. So now where's water going to move? Water is going to move to an area of where there is higher osmolarity of non-penetrating solutes. In this case, that is inside the membrane. And the key is water can move through the membrane. If water can't move, then water can't even go in, and we won't have any osmosis to take place. But sucrose cannot move, so it's a non-penetrating solute. It is osmotically active. water can move through the membrane, so water is going to move in. And basically what's going to happen to this membrane, or this solution inside, it's going to grow because sucrose can't move, but water's moving in. Basically, water's moving in to try to make these solutions equal in concentration, right? That's kind of the driving force here. Okay. Why do we care about this? We're going to care because imagine if this was a cell. Do you want water moving into your cell and expanding your cell? No, you don't. So we care about this osmolarity. In the very first lecture, we talked about homeostasis, not equilibrium. I did say one thing, homeostatic is equilibrium, is you want osmolarity to be at equilibrium. Osmolarity outside the cell, osmolarity inside the cell need to be the same osmotically, or else you're going to get the cell to shrivel or expand. Okay. So we can measure what's called osmotic pressure. And so if you have a membrane here, here's a solute. The solute can't move out. I have two columns. There's more solutes here, less solutes here of non-penetrating solutes. Let's make that distinction. But water can move through this membrane. Where's water going to move? It's going to move to the area where there is a higher amount of non-penetrating solutes. And so this goes up. If we wanted to measure osmotic pressure, we could put pressure down. The pressure that we need to push on this to keep the water from moving through here would be the measure of our osmotic pressure. Just realize solutions that have higher amounts, higher osmolarity of non-penetrating solutes have higher osmotic pressure. They're going to want to draw the water into them. Okay. All right, so now we got a new terminology. We're looking at tonicity. And tone, we're talking about the tone of the cell. It is related to osmolarity, but we got to take into account tonicity. We're talking about the tone's going to change because of osmosis. Okay, so we got to worry about whether the solutes are penetrating or not. All right, so tonicity has to do with, if there's no comparing osmolarities, what you're looking at is tonicity is what does a solution, if I put a cell in the solution, what happens to my cell? Okay, in an isotonic solution, right, there is no osmosis taking place. An isotonic solution means that the solution has the same amount of non-penetrating solutes as the non-penetrating solutes inside the cell. If they are equal, osmosis is not taking place. There's no net movement of water. And so the cells don't change size. B's over here. All right, these are your red blood cells. They're nice and round, biconcave cells. Now, we'll look at C. Got flipped around. A hypertonic solution. What happens in a hypertonic solution? Okay. The cells shrink. They do what's called crenate. They shrivel up. Okay. So let's look at C. Oops. This is a hyper. So a hypertonic solution causes the cells to shrivel. What would cause the cells to shrivel? Well, water leaving the cells. What do you think's in that? So here's my cell. I have a certain amount of non-penetrating solutes and my solution outside my cell. If I have more non-penetrating solutes in this solution compared to what's in the cell, where's my water going to go? it's going to go to the area of higher osmolarity of non-penetrating solutes. And so water leaves and the cell shrivels, and that is what is a hypertonic solution. Right? On the opposite end, a hypotonic solution causes the cells to swell. What kind of situation? What would have to be my concentration of non-penetrating solutes outside in this solution? All right, here's my cells, got a certain amount of non-penetrating solutes, and I'll tell you right now, the amount of non-penetrating solutes is kept homeostatic. The number of non-penetrating solutes that the cell keeps is roughly around 300. We use 300, it's really more like 296 milliosmoles of non-NP, non-penetrating solutes in cell. Okay, so now I have my cell. I have a solution that has less non-penetrating solutes than what's in my cell. Where's the water going to move now? It's going to move towards the solution with the higher non-penetrating solutes, which is in the cells, and that causes the cells to swell. A hypotonic solution causes the cells to swell. All right? So tonicity describes what happens to the cell volume. Isotonic, no change. Hypertonic, shrivel or crenate. And hypotonic, swell. If there's so much swelling, they're actually going to lyse. If we were doing this in the lab, we would do a experiment with this. If we'd look at the red blood cells under the microscope under, say, distilled water, which has no solutes, you would see no cells in there because they would all lyse up. So the difference between tonicity and osmolarity, remember we compared osmolarities of a solution, hypoosmotic, hyperosmotic, is osmolarity has units. Okay, tonicity, there's no units. All we're looking at is the tone of the cell. What does a solution do to the cell? It is related to osmolarity because osmolarity tells you whether osmosis is going to take place or not, but tonicity is just describing what happens to the cell in a solution. Okay. All right, so what are the determining factors for tonicity? Okay, tonicity of the solution, whether the solution causes a cell to stay the same, whether it causes a cell to swell or causes a cell to shrivel up, it's determined by solute concentration or the osmolarity. Okay, osmolarity comes into play in this because what we need to do is compare osmolarity between what's inside the cell and what is in osmolarity of the solution outside the cell. Okay, but the only osmolarity we care about is those that are determined by the non-penetrating solutes. Okay, so all we have to do is compare non-penetrating solutes inside the cell and the non-penetrating solutes outside the cell. If I have 300 milliosmoles, because remember the cell roughly contains 300 milliosmoles of non-penetrating solutes. If my solution has 300 milliosmoles of non-penetrating solutes, this will be equal to what's inside the cell's non-penetrating solutes. Okay, what would happen in this case? Would I have any osmosis taking place? No, there would be no osmosis taking place. Okay, because they are equal. All right, so all I have to do, I'm going to hammer this home, is that the non-penetrating solutes, I don't care about penetrating solutes. I can have penetrating solutes outside. I don't care, because if you think about it, the penetrating solutes are going to equal out on both sides because they can move through the membrane. Okay, so what I care about is the total amount of non-penetrating solutes outside the cell compared to what's inside the cell. And that is going to tell you where osmosis is going to take place, and whether osmosis takes place or not tells you the tonicity, because osmosis is either going to expand the cell or shrink the cell or keep it the same. Okay, let me go ahead and erase these and let's look at each of those instances. And let's see here. Boom. Okay, we already said 300. When comparing non-penetrating solutes in the cell, okay, if the cell has, in this case, solution and the cell have equal amounts of non-penetrating solutes, there's no water movement and that solution is isotonic. Right? What if the cell has a greater amount of non-penetrating solutes in the solution? So remember, the water is always going, osmosis is going to take place towards the solution that has the greater amount of non-penetrating solutes. In this case, it's inside the cell, so what's going to happen? Water is going to move in to the cell and swell it, and any solution that swells the cell is hypotonic. And then finally, if the non-penetrating solutes in the cells is less than what's in the solution, then where's the water going to move? It's going to move towards the higher area of higher non-penetrating solutes, which in this case is outside the cell, and that will shrink the cell, decrease its volume, and that makes this solution hypertonic. Okay, so I keep hammering down. It is the non-penetrating solutes that make the difference. Okay, the one that we'll see throughout the semester, the main non-penetrating solute is that of sodium chloride. Okay, sodium chloride is the most non-penetrating solute. Many times where you see sodium move, that's where water is going to move. Okay, we're going to see that because sodium is a non-penetrating solute. Sodium moves to an area, water is going to move into it. We're going to see this a lot when we get into the renal system and we're trying to reabsorb water and so forth. Okay, but again, non-penetrating solutes are the ones that matter. You put your little cell in here. Okay, P is for penetrating, N is for non-penetrating. You can see there is less non-penetrating solutes in the solution compared to the cell. So what's going to happen if I compare non-penetrating, where's the higher non-penetrating solutes? It's in the cell, and so water is going to move in and swell the cell. You can see with the penetrating solutes can move inside. They're going to equal out. Penetrating is going to equal and penetrating is going to equal inside the cell compared to outside the cell if they can move, because those penetrating solutes are going to move by diffusion. They're going to move to where there's less of that solute. All right, so they just equal each other out. So really the only thing we care about is the non-penetrating solute. Right? Again, here's rules for determining tonicity. And what do we care about? Non-penetrating solutes. Okay. Determine tonicity by comparing non-penetrating solutes to the solutes in non-penetrating solutes in the solution compared to non-penetrating solutes in the cell. Okay. So let's kind of we'll move this around and we'll talk about what's what. When the membrane is permeable to water, but not glucose or NaCl, what happens? Okay, this is a little disfiguring because it's showing, just look at these numbers here. What is our permeable to water, but not glucose or NaCl? Okay, this is a hypothetical situation. This is to get your mind wrapped around it, because later on I'm going to show you glucose is considered a penetrating and NaCl is not. But in this case, let's just make sure you're understanding the non-penetrating part. I'm making glucose cannot penetrate this membrane, nor NaCl can. Okay, it's an osmolarity, so we can compare the solutions, and that'll tell me where water's going to go. All right, and these are both non-penetrating solutes. How about A to A? That would be 1 osmo of glucose, 1 osmo of glucose on this side. Which way is water going to move? Yeah, it's not, because they're equal. They're equal on each side. How about A to B? Now we're talking 1 to 2. 2 over here. Where's the higher amount of non-penetrating solutes? Since glucose is considered non-penetrating in this example, which way are we going to move? We're going to move towards solution B. How about A to C? Remember, both of these are non-penetrating, NaCl and glucose. Now let's compare the osmolarities of the non-penetrating solutes. 1 to 1. It doesn't matter that they're different solutes, it has to do with the osmolarity. 1 osmolarity to 1 osmolarity, and they're both non-penetrating. So neither of those solutes are going to move across. Therefore, there's no net movement. B to B equal, again, no net movement. B to C, now which way are we going to move? Both of these are non-penetrating solutes. I got 1 osmol in the C solution, 1 in the B solution, so it's going to move towards solution B. And then C to C are equal, so again, no net movement. Okay? So let's look at, you have this chart in your book also, osmolarity. Remember, osmolarity is just comparing the osmolarities. Okay, we can have solutions with both non-penetrating and penetrating solutes. But which ones are going to determine osmolarity? Only the non-penetrating. So osmolarity is telling you I'm comparing osmolarity of the solutions. Before I put the cell in the solution, what are the osmolarities? If I have a solution, okay, my cell's what? 300 milliosmoles of non-penetrating. Okay, you can see a hypoosmotic solution. What would be a number for a hypoosmotic solution? Let's say 200 milliosmoles. Let's say all those are non-penetrating. I still compare 200 to 300. All right, which one's going to have higher osmolarity? All right, it's going to be the cell. It's always going to be the cell because 200 is always lower than 300. So this hypoosmotic solutions are always hypotonic to the cell. Now, if I look at an isoosmotic solution, this is telling me that the solution is 300 milliosmoles because it's the same as what's in the cell. Now I can be hypotonic and isotonic. How can that take place? Well, remember when we consider tonicity, we got to consider the nature of the solutes. Right? I can have 300, if my 300 milliosmoles is non-penetrating, let's compare non-penetrating. 300 in the solution, 300 up here in the cell. It's isotonic. No water's going to move. The cell's not going to shrink swell or shrivel. What if I have, so this solution, we know it's 300 milliosmoles, but what if 100 of these milliosmoles is penetrating solutes, P for penetrating? That leaves only 200 of the 300 as non-penetrating. Let's compare non-penetrating solutes. 200 to 300. Where's the water going to move? It's going to move towards the 300 milliosmoles that's in the cell. That would swell the it will swell the cell. And so what is that kind of solution? When the solution causes a cell to swell, it is hypotonic. All right, let me erase these so we're not so messy up here. All right, now let's look at a hyperosmotic solution. Hyperosmotic solution, I'm just going to throw you out a number, 500 milliosmoles. All right, what if that 500 milliosmoles is all non-penetrating? Compare 500 non-penetrating in the solution, 300 in the cell. Where's the water going to move? Into the cell, and that's going to out of the cell. It's going to move towards the 500 in the solution. That's going to shrivel the cell up. A solution that shrivels the cell up is a hypertonic solution. Now, I have 500. What if 200 of it is penetrating and 300 milliosmoles of the solution is in non-penetrating? What do I got to compare? I only have to compare the non-penetrating to determine the osmosis. 300 to 300, it's equal. There's going to be no net movement of water. It is isotonic. And then finally, the hypotonic, let's say 200 is non-penetrating, and 300 of that 500 solution is penetrating solutes. What do I need to compare to determine osmolarity? 200 compared to 300, what's going to happen? Okay, the water is going to move towards the cell, inside the cell. When a solution causes a cell to expand, that is a hypotonic solution. All right, so you can see how the osmolarity does come into a factor, but the only osmolarity we care about is the non-penetrating solutes. That's all you got to simply do. Compare non-penetrating solutes inside the cell compared to non-penetrating solutes in the solution, and that tells you where the water is going to move. All right, so now let's take this information and use it in the medical setting. All right, let's look at some IV solutions and why this is actually important, why this concept of osmolarity and tonicity is important to us for a medical sense. Okay, saline. Saline is a solution of water and NaCl. Remember, NaCl is going to be the most important non-penetrating solute in our physiology. So saline, NaCl, consider it a non-penetrating solute. Okay, solution is also known as normal saline. This is telling you what the osmolarity of the solution is. It is isoosmotic. Okay, so what do you think the osmolarity of the solution is? If it's isoosmotic to the cell, what is the osmolarity in the cell? 300 milliosmoles of non-penetrating solutes. So it's isoosmotic. This solution is 300 milliosmoles. If I was to calculate this solution, I would calculate, even the 9% would come out to roughly 300 milliosmoles. This solution is isotonic because isoosmotic, it's 300 milliosmole, and what's it made of? It's made up of all of NaCl, so all of the solution is non-penetrating solute. 300 non-penetrating solutes in the solution, 300 in the cell. That makes, so if I was to put my cells into this 0.9% saline, they would stay nice and healthy and round, and because the solution is isotonic. All right, now let's look at the next one down. 5% dextrose. So now we have this normal saline, which is how many osmoles? 300 milliosmoles. And I'm going to tell you, since down here you can see 5% dextrose is isoosmotic, so this is also 300 milliosmoles. So this total solution, this solution has an osmolarity of 600 milliosmoles. That makes it hyperosmotic. But when we actually put the cells in the solution, what happens to the cells? They stay the same. Stay nice and round there because the solution is isotonic. And why is this? What's this tell you about the character or the nature of dextrose? Is this a penetrating or non-penetrating solute? I'm going to let you know dextrose can be considered a penetrating solute. So do we care about the osmolarity of the dextrose? Does it matter for osmosis? No, because it is a penetrating solute. So all we got to look at is the osmolarity from the 300 from the saline, and that tells me, hey, 300 is equal to 300. There's going to be no net movement of water, and my solution is isotonic. Okay, so that is why the non-penetrating solutes. Okay, consider it in this example. Let's look at dextrose in water. Okay, dextrose in water, isoosmotic. So that tells me this solution is 300 milliosmoles. But what did I tell you about dextrose? It can be considered a penetrating solute. All we have is dextrose and water. There's no other solutes in this solution here. So how many milliosmoles of non-penetrating solutes do I have in this solution? There's nothing else in it but a penetrating solute, so there is 0 milliosmoles of non-penetrating solutes in this dextrose and water solution. So where's the water going to move? Yeah, it's going to move from the solution, that's 0, into the cell, that's 300, and now we get the cells will swell, and we have a hypotonic solution. Okay, so again, this is why this is important, but all we got to care about is the non-penetrating solutes. All right, so this is in part 1. I will continue on in part 2. We'll start moving into the protein-mediated movement through the membrane. But this gets us through simple diffusion and osmosis, and now we'll carry on with the rest of these in the part 2 of this lecture.